Hello everyone, my name is Krishnavardhan. Today I am going to present my course project on infrastructure health monitoring. My topic is on identifying damage in steel using different piezo configurations under the guidance of Professor Vishalakshi. The aim of the project is to identify the damage on steel member using piezo with different configurations. Here I am using three types of piezo configurations. One is bonded, the second one is changing the thickness of the piezo epoxy coating, third one is non-bonded piezo. The objectives of the project is to measure the extent and location of the damage. For the purpose of identifying the damage, a comparison study was conducted between bonded, thick epoxy bonded and non-bonded PZTs. First and foremost, this is my complete framework. This is made up of one long steel section and three cross steel sections. The longer one is 500 mm long and the smaller steel sections are each 200 mm long. These steel sections are held together by using bolts. Now we'll look into the procedure of the experiment. Make a mark where PZT should be connected. Clean the surface with sandpaper, then clean it with acetone to remove any remaining debris. Put on gloves and mix the two epoxies evenly before applying the epoxy to the element's surface. The coating of epoxy should be thin so that the PZT does not shear from its original position for bonded. Place the piezo on the epoxy and carefully push it down. For good bonding, place some weight on the piezo and leave it there for 15 to 30 minutes. We must attach the wire to the piezo using soldering. When the bond is complete, take 3 to 4 feet wire and apply soldering to the copper wire. Cover the positive electrode when soldering. Apply solder to the wire at the negative electrode. Create the positive electrode center and attach the wire to it as well. After soldering, cover the wire with tape to prevent the sensor and the wire from detaching. After the soldering, piezo must be tested for functioning. The wire of the assembly are connected to the electrode of the LCR meter for this. When a frequency of 10 Hz is applied, a humming sound or the vibrations of the piezo can be heard. This demonstrates that piezo performs admirably as an actuator. The wire of the assembly are connected to the electrodes of the oscilloscope using an oscilloscope. The structure is given some vibrations and we can see some electrical frequency created on the oscilloscope, confirming that the piezo is functioning properly as a sensor. The sensor is ready to use for monitoring after successful testing of piezo for actuator and sensor application. Apply a thick coating of epoxy on the top of the piezo after the test to protect it from harm. The same method is followed for thick epoxy bonded with the increasing thickness of epoxy layer. The same procedure is used for the non-bonded sensor, but it is done on a thin steel sheet, and this sheet is attached to the structure by bolting. Next, we look into the thickness of each piezo configuration. It is measured by using vernier calipers. For bonded piezo thickness is 0.1 mm. For thick epoxy bonded piezo thickness is 0.46 mm. For non-bonded piezo the thickness is 0.1 mm on the steel sheet. The sheet is attached to the structure by bolting. Now we will look into the methodology. A visual comparison of the pre-damage and post-damage signature is one technique to determine the structure's health. By using EMI technique approach, collecting the admittance data for the structure at different locations. First, by sending high frequency signals to the structure, then piezo actuates the structure. The same piezo will act as a sensor to sense the reflected signals. However, in order to quantify this change in the form of numerical index, statistical procedure must be applied. As a result, the raw data for the EMI approach is processed using the RMST technique to identify the location of the damage. Here you can see the RMST formula and it will be in percentages. Now we'll look into the experiment. This is the entire of my framework. First, we'll look at the bonded piezo sensor. The thick epoxy attached piezo sensor and non-bonded piezo sensor will be shown next. I have now placed my structure with the assistance of two supports. Next, I am attaching a bonded piezo sensor for testing and giving a frequency range from 30 kHz to 300 kHz using an LCR meter. The conductance and susceptance signature are now plotted in the Wipro software. The plotted data is recorded and the connection wires are relocated to a thick epoxy piezo sensor. Repeat the technique for thick epoxy bonded with the same frequency range and collect the data. The process is repeated for non-bonded sensor and the data is saved. Now by applying torque to the bolt we are inducing in-spin damage. This in-spin damage is given to all bolts and the process is repeated from bonded to non-bonded and the conductance and susceptance signatures are collected. We are inducing moderate damage by applying more torque to the bolt and the data for these three piezo sensors are recorded. We are now introducing severe damage to the bolt by applying torque to it and the data is being recorded for three piezo sensors. Now the baseline signature for conductance is seen here. Conductance is the real part of admittance. Here we can see three types of piezo configuration: bonded, thick epoxy bonded, non-bonded. For different piezo configuration, how the peaks are varying, we can see in this graph. This is the baseline signature for susceptance. The susceptance is the part of admittance indicating the health of the piezo patch. The susceptance graph should be approximately around 45 degrees angle so that the piezo is in good health condition. The three piezo configurations susceptance graphs are in approximately 45 degrees, so it indicates that the piezo is in a good healthy condition. This is the in-spin damage conductance. After applying some torque to the bolt, we are introducing some damage to the structure. So here different piezo configurations are bonded, thick epoxy bonded, non-bonded. Here also we can see the variation in peaks. This is the in-spin damage susceptance. The angle is in 45 degrees, so it indicates that it is in good healthy condition. Now the moderate damage conductance. It is for three piezo configurations: bonded, thick epoxy bonded, non-bonded. The shift of peaks, how it is varying for individual, can be seen here. Moderate damage susceptance. The peaks are at 45 degrees angle, so indicates that for moderate damage also the sensor is in good healthy condition. After inducing severe damage, the severe damage conductance looks like this. It is for three piezo configuration. The shift of peaks can be seen here. This is the severe damage susceptance. The angle is maintained at 45 degrees, so it indicates that for severe damage susceptance also the piezoids are in good healthy condition. Here we can see the RMST for bonded. The types of damage: instant damage, moderate damage, severe damage. These all three compared with the baseline, and we got RMST percentage around 15%. RMST for thick epoxy bonded. Types of damages are instant damage, moderate damage, severe damage. It is compared with the baseline signature of thick epoxy bonded. The percentage is around approximately 19 to 20%. RMST for non-bonded. The type of damage is instant damage, moderate damage, severe damage. These three damages are compared with the baseline signature of non-bonded. The RMST percentage is around 3.9. Now we move on to results. The results of RMST for bonded, thick epoxy bonded, non-bonded. From these three, we can say that the variation for non-bonded is very less compared to bonded and thick epoxy bonded.